So I'll be presenting the paper on the parameters complexity of almost stable matching. This is a joint work with Shushmita, Pallavi, Saket and Mera. So let's get started. So the problem, so to understand the problem, we first look at the model. So this is called matching under preference. So what we have is two sets of agents and disjoint sets of agents, and we want to assign the agents from one side with the agents from the other side. So this could be, examples could be assigning junior doctors to hospitals, students to colleges, etc. Now here generally the doctors have a preference over the hospitals given that which hospital is better, which is close to their houses. Similarly, hospitals also have preferences over the doctor given their previous performances, etc. And similarly for students and colleges, so we see that one side of the like one set has a preference over the other set, and it could be a preference over the subset of the other set. So doctors just give preference over a subset of hospitals, right? So this kind of problems are called bipartite matching problem with two-sided preferences, because you have preference on both sides, like the doctors also have preferences and the hospitals also have preferences as well. And as I said, that each agent in one side give a strict ordering, a strict linear ordering, which we call the preference over a subset of the other set. Okay, and we assume that every agent is individually rational, which means that they would prefer to remain unmatched than getting matched to someone who is not in their list, so who is not in their subset basically. So this is the basic model that we'll be working on. And now let's see what is a stable matching. So you have two sets of agents, as I said. One is denoted by this 1, 2, 3, 4, other is A, B, C, D. And classically this problem is known as stable marriage problem, where one side is basically denoted by men and the other is women. So as you see in this example. So, and each side has preference over the other, each agent in one side has preference over the other side, that is the other set. So here the agent 1 have preference A, B, D, C, which means A is his first preferred woman and C is his last preferred woman. Similarly, woman A has this preference 1, 2, 4, 3. 1 is her first preferred man and 3 is her least preferred man. So now this is how the preferences are here. And now let's say this is an assignment between the men and women. And we ask that is this stable matching? So now this, if you look at 4 and C, okay, so they prefer each other over their current partners. What do I mean by that? So 4 is matched to D and it prefers C more than D, and 3 is matched to C is matched to 3, but it prefers 4 more than 3. So they prefer each other. So this red edge, if we have such a red edge, this is what we call blocking edge. And if we have a blocking edge, the matching is not stable. So matching is stable if you do not have a blocking edge. Okay. So for this particular instance, for this particular set of agents and preference list, we have this matching, which is a stable matching, and you can check this by checking that there is no blocking edge here. Now the preferences here are a linear ordering, strict linear ordering over the complete other set, right? It's not over a subset but over the whole set. So if it can be over a subset, in general we can assume that our agent does not list the whole other side, okay? And this could be an example of such a preference profile where you have agent 1 only ranks A and B. That means he would prefer to remain unmatched than getting matched to anyone other than A or B. Okay, and A is his first preference, B is his second preference, that is the last preference. So if I have such a preference list, then this is the stable matching here. And as you can see that half of the agents here are actually unmatched. Okay, so if you have such incomplete preference list, the previous example we saw is called complete preference list, this is called incomplete preference list. So if you have such incomplete preference list, then a stable matching may not be perfect. And in fact, it can have size half the size of a maximum matching. Okay, so stable matchings are always maximal, so that also tells you that it can have half the size. Um, so, but then this is we are wasting a lot of resources here, right? If this is like assigning hospitals to doctors to hospitals, then many hospitals and doctors both remain unmatched, unassigned, right? So can we do a better allocation? Can we find, can we match more people, more agents, right? And but the fact is that if we want to find a stable matching, any stable matching matches the same set of vertices. So that means can not only we can't increase the size, but we cannot match a different set of agents either. So what can we do here? So okay, we can sacrifice stability to increase the size, but by how much and how do we measure the sacrifice? So how do we define stability? We define stability by saying that excuse me, that there is no blocking edge, right? So if there is no blocking edge, then it is stable. So we sacrifice stability, that means we allow a small number of blocking edges. Okay, and this is the measure of how much stability we're sacrificing. But okay, so let's define this problem formally. I have this graph, bipartite graph, G, A union B, and they have preferences as you saw in the previous example, and we are given two integers k and t, and now we want to find a matching which has at most k blocking edges. Okay, it's not stable anymore, it has at most k blocking edges, and the size is at least t more than any stable matching in G. So as I said, that every stable matching in G has the exact same, matches the exact same set of agents, so it has the same size, right? So I want to increase that, I want to find a matching whose size is T more and has at most K blocking edges. So this is the problem which is known as almost stable matching problem, because we are allowing a small number of blocking edges, and and we want to increase their size. So this problem is known to be NP hard. Not known. This problem basically we show that this problem is W1 hard, parameters by T plus K, and in a graph which maximum degree 3, and this is a polynomial time reduction, so we get that this problem is NP hard as well. And so this problem is hard. So what can we do? So let's to understand what we can do here, let's look at some properties of stable matching. So as we saw that okay, there could be so given a stable matching instance, there could be many stable matchings. There is not necessarily one matching, and one stable matching you can find in linear time. Okay, some particular type of stable matching you can find in linear time, but if we allow a small number of blocking edges, that is the almost stable matching problem. This cannot be done in polynomial time anymore. In fact, it is W1 hard with respect to KAT, right? And as you saw before, that every stable matching matches the same set of agents, but the agents have preference over stable matching. So what do we mean by that? Every stable matching matches the same set of agents, but suppose say here you have 5 men and 5 women, and this black matching is a stable matching between them. You can check that. It don't need to. This black matching is a stable matching, and again the blue matching is another stable matching between this same set of men and women, and you can check that every man gets a better partner into this black matching, and similarly every woman gets a better partner into this blue matching. So the agents might like one matching over the other. Okay, so now suppose I have a favorite stable matching, or you have a favorite stable matching, and now instead of asking that can I get a matching whose size is T more and has at most K blocking edges, I want to reduce the search space. I'm saying that okay, I want a matching which is close to my favorite matching, because this is the matching I like. So I want a matching which is close to my favorite matching, and it's not too far in, like it does not have too many blocking edges, and it also matches more agents, right? So now what we mean by it's in the close proximity of my favorite matching. So we can think of a matching as a 0, 1 vector, right, of length n choose 2, and so the edges are ordered in the graph, and you put 0 for the edges which are not in the matching, 1 for the edges which are in the matching. So you can write your favorite stable matching as this 0, 1 vector, right? And I want to, so in the close proximity could mean that I want to find a matching which has a not very large Hamming distance from this particular matching. So each matching, for each matching I can write this vector, right? And I do not want, I want a matching which has a small Hamming distance from my favorite stable matching. Okay, now so the question is that can we at least find this matching, because we have reduced our search space now, so can we at least find this matching efficiently? So again we define the problem formally. Again the input is same, the graph A union B, but you have a stable matching given now, which is your favorite stable matching, and you have an extra value Q given. So if you think for a minute, you would see that it does not have, so the way I define the Hamming distance, it does not have a large Hamming distance. Actually boils down to saying that it does not have a large symmetric difference with this matching M. So I want to find a matching M star whose size is T more than M and has at most K blocking edges, and its symmetric difference is with M is at most Q. Okay, so we want to find such a matching M star. Now can we do this efficiently? Sadly, this problem is also NP hard, and not only that, this is W1 hard. Again, this is a polynomial time reduction, parameterized reduction with parameter. So this is W1 hard with parameter K plus T in a maximum degree 3 graph, and this is W1 hard when parameterized by K plus T plus Q as well. But this is FPT when parameterized by Q plus D, where D is the maximum degree of the graph. Okay, so if I so this is the algorithm that we will be seeing today, and I will give this is a deterministic algorithm that's given in the paper. I'll give a randomized version, so we'll get a slightly better running time, but it will be randomized. Okay, so what is the intuition? How do we go about finding such a matching? So you are given, now you are given a stable matching, your favorite stable matching, right? And suppose this black zigzag lines denote the stable matching, and what you want to find? You want to find a hypothetical matching M star whose symmetric difference is bounded, right? With whose symmetric difference with M is bounded. So suppose these blue edges are the symmetric difference edges, okay? And so how do you get M star? You alternate along this symmetric difference, this alternating cycle and this augmenting path from M, right? So M is the zigzag edges, right? And the M star edges would be this blue straight line edges and this black zigzag edges. Okay, so suppose this is your hypothetical solution, and then if I have this blue edges, I can find M star, right? Because these are the symmetric difference edges, I will just take the symmetric difference with M. Okay, take these edges, do symmetric difference with M and get M star. So this is what our goal would be. We want to find this symmetric difference edges. So now, okay, so now this black thin lines are some other edges of the graph which are not in the symmetric difference, and I'm just showing this to show that the matching M star suppose has here 3 blocking edges. Okay, so it can have blocking edges, right? Because it is not stable anymore. But M was stable matching, but hypothetical solution, the solution that you were looking for, the matching that you were looking for, has blocking edges. Okay, so now with this intuition in mind, let's go into our algorithm. So the first step we do is we want to identify, or we want to highlight the symmetric difference vertices. What are the symmetric difference vertices? The endpoint of the symmetric difference edges. Okay, so the endpoint of this blue edges. So we highlight them with color green, and we want to separate them from the remaining vertices. So we call their neighbors as border vertices. Okay, so any neighbor of green vertex, such as here U5 is neighbor to W2, it's called a border vertex, and their partners we call border mates. So to separate the symmetric difference vertices from the remaining graph, we want to color this border and border mate vertices with blue. Okay, so this is what we want to do. So what we do is that uniformly at random we color the vertices of the graph with two colors, green and blue, and we want the symmetric difference vertices to be green and the border and border mate vertices to be blue. Now what is the probability with which the symmetric difference vertices would be green? That is how many symmetric difference vertex you can have. The symmetric difference number of edges in the symmetric difference is q. So you can have at most 2q vertices. So this probability is at least 1 by 2 power 2q. And how many neighbors you can have, such blue neighbors, like how many border vertices you can have. So recall that the degree of each vertex is bounded by d. That means you can have at most 2qd many border vertices, that is 2qd many neighbors of the green vertices. So the total of border union border mates would be 4qd. So this probability is at least 1 by 2 power 4qd, right? That this vertices are colored blue. So after we do this, we want to focus on the graph induced on the green vertices. Okay. So now what did we achieve here? So all this, if our coloring like with this much probability, we have colored all these vertices green. So all the endpoints of the symmetric difference vertices green. So if I look at the graph induced on green vertices, we are looking at, we definitely have separated out the symmetric difference vertices from their neighbors, right? So now, okay, so now two things we achieved here, or two things we should note here, is that one is that any blocking edge, for any blocking edge, one endpoint has to be green, and this follows from the fact that your M matching was stable, okay, and if you look at the components of the G green graph, the graph induced on the green vertices, then there is all the edges that are going between two different components of your graph, they cannot contribute to the symmetric difference. Neither they can contribute to the increase in the matching size, like the solution matching size, or they cannot contribute to the blocking edges as well. So this I will not prove, but this is what we achieve after the vertex separation phase. Okay, so now we will focus on the components of the graph G green. Okay, so we have so this is what we have done, and now are we done now? Can we now find the solution? Find a solution, right? So we know the symmetric difference vertices. So we know this green vertices. Now I'm looking for an alternating path, or maybe some alternating path cycle. So there I get an alternating path, augmenting path here. This blue path, right? It starts from U4, goes to W2, then U2, then W1, then U1, then W3, U3, and W4. So this is an augmenting path, and then if you alternate M along this augmenting path, it does increase the size, but it has more blocking edges. Okay, so it can be that you find an symmetric difference edges given the vertices, and you found and it increases the size as well, but it increases the number of blocking edges as well, or it could be the other way also. So finding the vertices, it's good, we have achieved something, but this is not good enough to find the solution or find the symmetric difference for edges yet, because we said in the first, right, that this is our goal now, we want to find symmetric difference edges. So now what do? We color the symmetric difference edges as well. So this is the edge separation phase where we want to identify the symmetric difference edges as well. So we color the symmetric difference edges, okay, every edge in M symmetric difference M star with blue, and every edge which is whose both endpoints are green but not a symmetric difference edge, we color them with red. Okay, and everything that goes uh, out of this G green, so that is one endpoint is green and another endpoint is something else, then we color it with magenta. Okay, so here this vertices will also be colored in the vertex separation phase, but as I have kept them gray because we don't know how they will be colored, right? Because every vertex was colored green on blue in the first vertex separation phase. So now now okay, we did this, but how about how much so we did this coloring uniformly at random with this blue and red colors uh, in the graph G green, and what is the probability that we colored the symmetric difference edges with blue? So we have at most q symmetric difference edges, so this probability is 1 by 2q, right? And how many red edges you can have? You can have at most 2qd red edges, so this is 1 by 2qd. The probability is at least 1 by 2qd, right? So now we have identified the symmetric difference edges separately, and so we look at each of the components of the graph G green. Now inside each component, I identify that I look at the green, look at the blue edges. Those are the symmetric difference edges. So I count how many symmetric difference edges are there. That is denoted by Qi, and then I count how much size is increasing. So basically, I see how many augmenting parts are there, and that is denoted by Ti. And Ki is the number of blocking edges that is incident on the component Ci. So this is a bit subtle how to compute Ki, but since I said that after the vertex separation phase, no edge which goes between two different components contribute to a blocking edge, is a blocking edge. So it's not like no edge which goes between two components is a blocking edge. So we can, for each component separately, we can compute this value Ki, and now our problem is that we want that the sum of ki's over the component over the components, right? C1 to Cl, is the sum of ki's. So we want to we want to find a subset of these components such that in those components the sum of ki's is at most k, and sum of qi is at most q, and sum of ti is at most t, at least t, right? Because we want to increase this thing, and we want to increase ti, and we want to minimize qi and ki. Okay. So now this is exactly the problem which is called two-dimensional knapsack problem, where you want to increase, you want to minimize two quantities and maximize the profit. So this is exactly the same problem, and we have this is we have a pseudo polynomial time algorithm for this, and here all your quantities are bounded by our parameters. So this gives us a polynomial time algorithm to find a subset of these components. Okay, so now I have the subset of this component. So I identify the qi edges, that I identify the blue edges in those components, and those are the symmetric difference edges. So I take alternate along those edges, and I get a solution, right? So this completes the algorithm, the procedure of the algorithm. Now what is the how much time is spent? So this runs in polynomial time, but we did randomly colored those vertices and edges. So we need to repeat the process to boost the probability, right? So here we spent 1 by 2q. The probability was at least 1 by 2q. Here it is 1 by 4qd, and here it is 1 by q again, and 1 by 2qd. So it's order qd, right? So 2 power order qd time, if we repeat this algorithm, right, with good probability, we find this blue edges, and that is the symmetric difference. We find the symmetric difference edges, and hence we find the solution. Okay, so this completes the algorithm. I will end the talk with some open questions. So as I said at the beginning, that we want to allocate more people, so we want to increase the size of the matching, and to do that I have to sacrifice stability. So this kind of problem is called size versus stability trade-off. Now we also saw that there could be many stable matchings, and one stable matching could be preferred by some agents. So there could be a satisfaction value, like how much satisfied the agents are, and there could be some matching which satisfies more agents, some matching which satisfies less agents. So how about satisfaction versus stability trade-off? So like I want to find a matching which is close to stable, that is a small number of blocking edges, and satisfies attains maximum satisfaction for each of the agents, or attains a minimum value of satisfaction for each of the agents. Okay. Another problem could be generalizing this almost stable matching problem from size to maximize the utility function. So this is also on the same line as the previous question. So instead of having ranking, ordered ranking, you have utility function of each of the agents, and now you want to maximize the utility of the utility of the total utility, the sum of total utility uh, in your of your matching, and for that you are ready to sacrifice the stability of it. So these are the two immediate open prob questions that could be looked at from here, and that's all. So thank you for your attention, and if you have any question, you can write me here or you can ask me in the question and answer session. Thank you.